Hi, everybody. This is David Paul, and we're here to talk about the low pressure UV Aquafine ink. Today, it's going to be me giving a little introduction and then Simon Tarlowski from Aquafine doing the rest. This is the third part of a three-part series on UV. We've already done the previous two. If you didn't attend those and want to see it, we have it pre-recorded and will be on our website. So this is going to be a 45-minute presentation. I'll give 8 minutes about of intro. Simon will give 35 or so minutes on the details of his UV. And then we have 15 minutes of question and answers. So just type your question anytime into the question box or the chat box, and then we'll get to that at the end. As you exit this webinar, you'll receive an email, and there'll be 3 questions. It'll only take a very short period of time. So please answer those questions so we get some feedback of what you thought of this webinar. This presentation is recorded and it'll be available next week on our website. And you'll also receive a thank you email in the next day or two with a PDF of this presentation. So all the slides that you see, you're going to get a PDF of those slides. So just for your information, no money changes hands on DHP webinars. DHP and Aquafine don't have a financial relationship. So we just present these because we think they're of value to our industry. I've been working in water treatment for a lot of years, high-tech water treatment, including reverse osmosis and UV. Been training consulting for many years, have a Master's of Science in Microbiology and ROS 4 certified with David Paul Inc. Simon, who's going to give the bulk of the information today, he's the corporate director of Aquafine's Integration and Diversification. He has a degree in chemical engineering. He has other degrees, and he's also going for a PhD. So got a smart guy today. And he has really excellent experience, a lot of years of experience. I'm just going to give a real brief overview of ultraviolet irradiation. UV is between X-ray and visible. So what we see is going to be wavelengths that are greater than 400 nanometers. UV is in that 100 to 400 nanometers. And what we're talking about for nanometers is just the length of the wave in nanometers. So scientists always trying to figure out, how are we going to make a buck off of electromagnetic spectrum? Well, they found that X-rays won't go through bones, but go through soft tissue. So that's how we can look inside of a body and see bones. So that's a use of X-ray. Well, they looked for this, how they could use UV radiation, and they found that UV can destroy organic molecules, TOC, total organic carbon, with a maximum effectiveness of maybe 170 nanometer wavelength. And ozone and chlorine could be destroyed at a wavelength, 254, 255. That's the maximum effectiveness, and that you could inactivate bacteria maximally at a wavelength of maybe 260, 270. All right, so then scientists look for how do we create UV radiation that we want? Well, if you energize sodium, Na, it just gives out visible light, so that doesn't help. If you energize potassium, K, that just gives out visible light, that doesn't work. But if you energize mercury, Hg, you actually do get UV light. So we're going to see that these UV lamps have mercury. So there are 2 flavors, low pressure and medium pressure. The low pressure UV, which is what we're going to talk about today, they're primarily 2 wavelengths produced, 185 nanometer, and that's going to be used for TOC destruct, organic destruct, and 254 nanometer, used for bacterial inactivation and ozone and chlorine destruct. So a low pressure lamp is going to put out the 185 nanometer and 254 nanometer, about 5% 185, about 90% 254, and the rest is going to be scatter. So if you want a 254 nanometer lamp and you don't want 185 coming out because you don't want the organics being destroyed because that'll increase your conductivity, then they'll put a dopant inside of the quartz of the lamps, and that will absorb the 185 nanometer. Can't come out. So 254 nanometer doesn't allow 185 to come out. And 254 nanometer used for bacterial inactivation and ozone and chlorine destruct. If you want 185 nanometer, then you don't want the dopant put into the lamp. So the 185 comes out, but also the 254 nanometer comes out. So you use the 185 nanometer for TOC destruct. But because the bulk of the UV radiation is not 185, only 5% is 185, usually the UV systems are going to be larger than for 254 nanometer, or they may put it next to a tank and recirculate the water through the UV to try to get as much dosage as possible. So it's important to know that a 185 nanometer lamp does produce the 254 nanometer, so it also can inactivate bacteria and destroy ozone and chlorine. Medium pressure UV, the last two webinars we did were on medium pressure. Medium pressure takes a lot more input energy, but it puts out a lot more output energy, but not all in the UV range. I mean, much of it you see is in the visible range, but the portion that is in the UV range is at a much higher intensity. So it's like one medium pressure lamp is equivalent to around 16 low pressure lamps. The HOD UV, which is what we went over in our first webinar, it is a medium pressure UV technology. And again, you can go to our website if you want to see the webinar on that. So let's just take a look at an example of UV pre and post RO. From my experience, I see pre-RO UV in the pharmaceutical and biotech industry more than probably any other industry. In this case, the UV may be just for bacterial inactivation, or it may be just for dechlorination, but it'll do both jobs. For post-RO, usually it is for TOC removal. So I'm giving an example here of semiconductor microelectronics, where we see a 185 nanometer UV after double pass RO, electrodeionization, mixed bed ion exchange. So now you've removed all of the ions, you've removed just about all the conductivity, but you want to get the TOC level low. So here's a 185 nanometer UV. And then if you want less than 1 part per billion of TOC, then you usually use ozone enhanced 185 nanometers. So you see ozone being put into the ultra pure water tank, and that comes out and goes to a 185 nanometer UV. So since 185 nanometer UV also produces 90% 254 nanometer, the ozone is then destroyed, so it doesn't go downstream and mess things up. And then typically just before the final filter, in this case an ultra filter, there's a 254 nanometer UV for bacterial inactivation. All right, so that's it for the intro, and we will now go to Simon's presentation, and his is going to be on low pressure.
Okay, thank you very much. I hope everybody can hear me. And you should be able to see my screen right now. Welcome again. This is Simon Tarlowski. I work with Aquafine, and I thank David for giving me a higher position in Aquafine than what I really have. I used to be director in other companies. But in Aquafine, I really deal with a region, and I am helping clients continuously. My client range includes lots of bottling plants, food and beverage in general. I have also clients in the microelectronics industry. That is one of the most important sectors that we take care of. And the UV has been spread into many, many applications. But coming to the point of this presentation, we are talking about different lamp types. and thank you, David, for the introduction. Because I want to take a moment to talk about a little bit of what is radiation. Radiation is when we energize, when we present energy that may be electrical energy, it may be light energy, it may be a laser. There are many ways to put energy into atoms. The electrons jump from one orbital to another, and when they come back to their natural orbital, they have a quantum value that is equivalent to the radiation that they emit. What happens with pure mercury is that we are fortunate enough that pure mercury, their quantum value for the jump of the electron from one orbital to another is actually the 254 nanometers. And that's very nice for us in the UV applications, because this 254 nanometer is the most poisonous radiation for the DNA in the cells. So UV coming out from pure mercury lamps, it's mainly 254 nanometers, as David was explaining. We also have a little bit from 185 that comes out, but most of the energy coming out from low pressure systems that are the most inexpensive lamps, most inexpensive systems to run, because it's just one single wavelength, and all of the energy actually goes where we want it to go. Is a fortune that it actually goes to this disinfection process. As you know, most companies, we deal not only with the low pressure lamps, and following David's explanation, we also have the high output lamps that can be either low pressure or high energy, where most of the time what we use is not pure mercury, but we create amalgams. And because of the amalgams, meaning the presence of other metals together with the mercury, that's where the quantums vary from metal to metal. So if you have some silver, you have some titanium, you have some gold, each one will be giving you energy in different nanometers values. And that's what you see in the graph that showed that there were many, many spikes. This is good and this is bad. It's good when you have a diversity of functions for the lamp to perform. It is bad because if you are just looking for one function, that is disinfection, you are going to waste most of your energy in non-disinfection wavelengths. So if your application, you are in an hospital, you are in a laboratory, you are in a beverage packing facility, and what you are interested is really deactivating the microbes, the best value for your money in the lamps will be the low pressure lamps, because 100% or really close to 100% of your energy is going to go to disinfection. Now, let's talk a little bit about the RO systems. And, you know, RO systems is a membrane system. And what it does is that it uses a membrane to separate from the high pressure side where you have your feed. Some of the water will flow into a low pressure side that is your permeate. And the membrane will keep your dissolved solids from crossing from the high pressure to the low pressure, up to typically 95, 98.5. 99% of the solids will stay on the high pressure side and will go to the other end of the system and leave as reject. So RO system can be for a separation as big as in seawater, going from 3% salinity water down to very, very low salinity, very low conductivity water that can be used for drinking or can be used for processes, or it can just be done for a softening, the ionization of water. The main problem that users of RO have is that the RO is not good enough for everything that you need, and sometimes the water that you are feeding into the RO is not good enough for the membrane to work, and you get into problems like fouling that can be biological or can be chemical. You can have problems like suspended solids in the water. If you have sand in the water going into a desalination plant, that's going to cause problems with the membrane. So an RO system is typically divided in pretreatment, then reverse osmosis separation, and post-RO, that is actually making that water that is too pure for many of the uses drinkable. Or in another cases, it's not pure enough for the uses as it goes, and it needs another treatment to even reduce further the salinity or the conductivity of the water. So we come to why do we need this? So in pretreatment, what happens? We have sand, it can perforate the membranes. We have other kind of solids that can form layers and actually not let the pure water go through the membrane. And that's why we do suspended solid removal, we do chemical conditioning, and chemical conditioning we do to actually control what the pH, what crystallization is going to happen as we increase the concentration in the reject. So we add some chemicals to avoid that crystallization happening on the membrane. And where UV comes in is in biological suppression. Many of you that are working with ROs, you do sometimes chemicals like chlorine to kill any algae, any bacteria, anything that can slime your system, meaning that can create a film of organics on your membranes that won't let the membranes let through the pure water as you want it, and then increasing your pressure in your system and reducing your recovery. One option of reducing the bio is also with UV, because as we said before, 254 nanometers will impede the reproduction on the membrane of those microbes that can cause films from going there. Now, other reasons that RO system fails, maybe on the RO, operational problems. We raise too much the pressure, we crack the membrane. We can have problems with the pumps. We can have problems with seals going bad. We can have crossing of bad water from the reject side to the permit side. And some of the solutions that we put in, like cleaning the membranes, sometimes they don't go good enough. Now, post-RO, when is your system failing and what can you do about it? So one of the problems that you have is you are not matching the standards. Maybe your RO is working very good. Maybe it's concentrating way beyond your design. One problem, maybe you are having too much hardness, too much salinity, too much minerals. So that's a failure of your operation. You have to moderate the operation of your RO to match what the standards are, what your controls are on the reject. Another problem that you can have with the RO is multi-stage balancing. Many times we have a one-stage RO, sometimes you have a two-stage RO. Most of the time, we are not in control of how much goes from the first stage to the second stage. Many times, the design is also failed, so your RO may be off balance. That's another problem where UV cannot do anything to solve. Other problems that we have in the RO is with the gasification. Many times you get CO2 levels going up in your RO system. This CO2 can actually make bubbles, and these bubbles can be interrupting the function of your RO. We do the gasification in those cases. Other problems that we have is when we remix, sometimes we put some of the feed stream back into the permeate stream to actually match what we want with minimum cost. And another problem we have that we can solve with UV is having good conservation measures to the permeate. The permeate, we treated it already for biology before it entered the RO. There shouldn't be any biology, any bacteria, any algae on that permeate, but it can get contaminated after the RO. And what we do is we put a UV there just to make sure that if accidentally any living microorganisms enter the permeate tank, we can actually annihilate them before they reproduce, because there might be nutrients or other in the water. So, coming back now to the RO systems. So we said UV will help before. It will prevent sliming. And if we use it instead of the chemicals, it will prevent us from using chemicals like chlorine. That chlorine actually perforates membranes over time. So if we use UV, we will also save membrane life, and we will also remove the need of taking out the chlorine that we used into the feed water by adding more minerals. And that's also less work for the RO membrane, because if you add bisulfate and chlorine to the water before it enters the RO, it is work that the RO will have to do to keep those dissolved solids in the reject side and not go to the permeate side. So it will also save you energy in the RO process. After the RO, that's where we were saying, okay, UV can help you prevent further infection of the permeate. But also, we have uses of the UV, as David was already saying before. If we still have TOC, and the microelectronics industry is very critical on what is still in the water that has been already purified, this TOC can be a pollution that can actually create encroachments and make the rinse of the tablets not be perfect. So we can use for TOC reduction. As David said, also, sometimes you use a combination of ozone with the UV. And what we do is that you use the ozone to do an advanced oxidation level in the water, meaning you will use oxidation to eliminate many atoms that are not desired and convert them into an easier treated compound. But you want to remove the extra ozone. UV will take care of that. So that's where we can use it. Now, there is one danger also to it. That is, UV creates peroxides. And when we create peroxides, we can also get in trouble for creating corrosion in the systems, in the piping, in the valves, down the line. So something that the UV companies are very careful is not to oversize, not to overdose. And in the 21st century, we are now seeing the first systems that are having dose control, that we can measure how much contamination we have before it enters the UV and actually graduate the dose to how much is needed. And with that, we are not going to have excessive peroxide formation that will kill your systems over time. Now, how the UV lamp works, I think we talked a little bit about it already. Just a quick review. Mercury has electron transitions, meaning electrons jump from one orbital to another. And with that, when the electron jumps back, it creates exactly at 253.7 nanometers. And that radiation is what comes down and destroys the DNA of the microorganisms. Important concepts that we need to know here. UV lamps, to have the highest emission, they have to be already hot. It's like a fluorescent lamp that you have in your office. You get more light when the lamp has been already stabilized. Most UV lamps need actually a warming period, meaning that while they are warming, you are not getting the radiation that was assigned or that was sized for your system. So there is a period of warming in most of the UV systems. I am sure you will have some questions about it. I will answer them later. Also, there is another factor in this, and a very common factor in this is you should be asking yourselves, what if the water that I am actually submitting to UV rays is too cold? The answer is, it's okay if the water is too cold, as far as the lamps don't get as cold. So if you have a lamp immersed in the water and it's getting cold because of the water temperature, that's something that you need to know when you size it. Also, you have some lamps that are in touch with the water. They will cool down farther. You have other systems where the lamp is inside a sleeve and there is air separating the lamp from the sleeve. Those lamps work better in cold environments. Overheating can also be an issue. Lamps may burn when they overheat. Also, systems have a prevention to that. So if the system gets too hot and you are on risk of creating water vapor that will also do more overheating, most of the UV systems have heat sensing switches and heat sensing alarms. So we take all of these in consideration when we are building a UV system. So this slide shows you some of the data. 90% in general of a low pressure lamp, 90% of the energy is dedicated to 254 nanometers. And this is what we want. The 185 nanometer wavelength, we can take care of it in two ways. We can do a coating inside the lamp, as David showed, or we can just let it be. Most cases, the 185 nanometer is not going to harm the water. For most of the purposes, drinking water from a facility, you are bottling water, you are Pepsi, Coke, Nestle, any of the companies that bottle water, the 185 is not going to hurt your product. And as I said before, UV output is sensitive to the water temperature. Now, the second part is answering some of the typical questions. How long does a lamp can a lamp be used? 8,000 to 12,000 hours is a standard. We check all of the lamps that we have. We have also lamps that we call them validated, that we test them for a period of time to make sure that the degradation curve of the lamp matches the expectation. When we talk about 8,000 to 12,000 hours, that's the range when we lose 20% of the intensity to the water. Lamps don't switch off one day to the next, but from the first time we connect them, we start losing intensity. Our expectation is that you can use a lamp for up to a year and still have enough energy to kill as much as your lamp was sized for. The pressure is low. The power density is less than 1 watt per centimeter. Temperature it's usually normal temperatures. We want it to be at 40 degrees C for most of the time. That's in the range of the 100 degrees Fahrenheit. Usually we put alarms on 180, 170 degrees Fahrenheit, so we know before we get to the boiling point of water. That is our main concern. Most lamps can withstand, no problem, hot cleanings. What we don't want is to degrade the plastics that are part of the UV lamp systems that can be degraded with higher temperatures. Now, what is a LPHO? HO means high output, meaning that we can still have low pressure in the system and still have many more watts. Not to say we are going to have 50 times as much energy coming out from one lamp as from an LP lamp, plain LP. But if we want to make it more intensive, if we can keep the number of lamps lower, we can go with systems that will give us higher output. We have in the LP range, meaning pure mercury lamps that can perfectly work with higher watts levels, meaning it's like having a fluorescent lamp. You are not limited that all your fluorescent lamps are 40 watts, right? You can have a fluorescent lamp for up to 200 watts in your office. And that's what we do. We have developed lamps that, being low pressure, can be the equivalent of 4 or 6 of the older LP lamps, and we call them high output. So when we size an equipment, we have either the choice sometimes to pick or one high output lamp being LP, or using a regular LP lamp, and then for some systems we can go with very few lamps. You know, you have systems that are single lamp systems that are actually the beginning of the price list and the beginning of your operation performance chart. Now, what is the difference when we go into an MP? We go into an MP, as we said, you have a wider spectrum. You have more than the 254. We use MP lamps most of the time when you have applications that so require, like reduction of some compounds that you want them to be reduced. We were talking chlorine as an example. So even an LP lamp has less energy. It has more dedicated energy, dedicated to disinfection. That's why LP lamps are usually the user's choice for disinfection application. This is, again, just for you. We really want you to remember the graph of what the wavelengths are when you have an LP lamp. You see, most of it is in the 254 range. You have some in the 185. And the main characteristic is that this is a pure mercury lamp. Compared to the wider range, similar graph to what David showed in the introduction. But just remember, depends what do you want your lamp for. If it's disinfection, if it is about avoiding the formation of biofilms, you don't need all of that energy. You can see that most of the energy is way above the 250 range. All of that energy that you are applying to your lamp is actually being wasted. Disinfection is not going to happen at those wavelengths. But if you want reduction of some compounds that actually get reduced at those levels, MP should be your lamp of choice. And we, as everybody, have all of them. Another subject that I have been talking about on and off is the aging. And the aging of the lamps, you can see in this graph. And you can also see the threshold of the 8,000 hours. How fast a lamp ages. You can see how much it ages, and you should be looking at how long is the life of a medium pressure, and then how long is the life of our lamp that is the low pressure. You can see that if you want 8,000 hours of life of a lamp, you go with the upper line. A medium pressure, you will have to change lamps more frequently. In the older systems, you used to change the lamps per recommendation. We have systems today that you have intensity meters. You should actually be smarter about knowing when do you change the lamp per the intensity meter, and that should be in reference to how the unit was sized at the beginning. So either you have an MP lamp, you have an LP lamp, you have to look at those sizing parameters. And in general, our recommendation is for systems that we give the clients that have intensity sensors that are very important to change lamps when the intensity is reduced to 80% of the value of the lamp. Most of the time, we size units to 80% as end of lamp life, that's what we call. And meaning that at the beginning, when you start up a new lamp, you have about 25% extra energy. You can handle 25% more flow or more microorganisms. But when you get to the end of life of the lamp, you will have not anymore that redundancy, meaning you are coming to the point where if your microorganisms are the same as size, your flow is the same as size, the recommendation is to change the lamp. We are getting now into smart lamp technology. That's what's coming now, and we have the first smart lamps. That means lamps that actually feed back to your control rooms and tell what the status is, how much intensity is coming, how much power is the lamp consuming. All of those parameters are going to be very helpful in the new systems for the maintenance and operation of your systems to actually know when to change the lamps, and also to look for problems like lower UVT, lower transparency, meaning less UV is getting to your intensity sensor, less is getting to your microorganisms that you want to control. So this box, this table, is just a brief, very, very brief comparison. You can see this table in detail. So when you see the table in detail, after that you'll see more or less comparison operation cost for LP amalgam, or the medium pressure lamp. You can go further on that and actually do your analysis, and we can talk about sizing also in your question and answer session. Okay? So applications, what is the lamp type that can be used? You can see actually that medium pressure is not recommended for chloramines. Low pressure is recommended all over, from disinfection, ozone destruction, VOC reduction, free chlorine, chloramines, chloramine control, chlorine dioxide destruction, and advanced oxidation processes. The power consumption will be way lower in a low pressure lamp than in a medium pressure lamp. The life will be much longer in a low pressure lamp, and this means that your system will be much less expensive if you work with low pressure than if you work with medium pressure. Some arguments that medium pressure takes to their favor is about footprint. They claim that medium pressure, because you use less lamps for more energy, you use less footprint. But being honest, I think we should evaluate in a case-by-case scenario. Let's size units, and we do that all the time. We size units for low pressure, and we size units for medium pressure. And then the application is what makes the selection. If we have a microelectronics plant on TOC reduction, many times we use the high pressure plant, the medium pressure plant. If we have clean slate disinfection for a beverage company, we do most of the time low pressure lamps for this disinfection, pre-RO, low pressure lamps. So as I say, it comes down to each application. We have software developed that actually helps us choose which lamps, which kind of systems will be the most economically efficient. And many times we do multiple runs. I just wanted to get closer, before we close the presentation, talk a little bit about the regulatory environment and actually about validation. There are two aspects of validation. There is instrument validation, or there is part of the equipment that gets validated like a lamp or a sensor. But there is also total validation for a system to work as it is. As you know, a system is made and is sized considering how much UV I need, for how much time I need to expose the microorganisms, and that will give me the information of how many lamps and for the flow, what size of system, what energy of system I'm going to have. If it flows faster, I have less residence time. If it flows slower, I have more residence time. So I can use a UV lamp that is acceptable to do it, to work in my system. So validation, who needs validation? Most of the validation is needed because of regulation. Most of the transportation, interstate transportation of beverages and also dairy products is federally controlled. And federal law requires validated equipment. We have validation certificates from all over the world. And for many of the applications when it's required, like the beverage industry or the dairy industry, we can give these certificates that show that actually an independent lab took our equipment and compared how much disinfection we got compared to disinfection done in a batch test. So here you have the graph showing the disinfection in the equipment compared to the disinfection in batch testing. And if we pass the test, means that our equipment did the same as the batch test. And that's what we are validated for. Okay, so I am going to just browse through while you write your questions. You can see a couple of pictures of typical installations that we have. And thank you for being here. We have 15 minutes to answer questions. And while you see some pictures of our equipment, David and Darrell, if you want to take control of the screen, we are about the 45-minute marker and getting ready for the 15 minutes of questions and answers.
Hello, well, thank you so much, Simon, for that information. And again, tomorrow, the next day, you'll receive an email thanking you for attending, and also you'll receive a PDF of all of the slides. So now we've got 15 minutes for question and answers. So if you haven't written a question and you have one, please write it now. Simon will then read the question and give the answers. And then at the very end, we'll give a minute of wrap up and then we'll end.
At this point, I see the first question that I got. It asks, when you say TOC destruct, what is actually happening? Meaning, what are the TOC reduced or converted to? Are they reduced to their elemental components, or to some intermediate form? Thank you for the answer, for the question. Actually, this is a very interesting subject. When a microelectronics mainly company is looking for TOC destruct, what's actually happening is that they are looking for the final elements that are still remaining in the water, and most of those elements actually came from the pollution in the rinse process, from the chemical additives that they add in the rinse process of the tablets, that are basically small molecule organic chemicals. And what happens is that if those elements are still there in the process, you can get some kind of carbon, some kind of graphite, things that may become impurities and change the quality of the tablet. You may have, what they are looking for is to reduce the number of defects in the circuits, in the microcircuits. And higher TOC has proven to make more defects in those circuits. Now, when we destroy it, the goal actually is to get all the carbon to CO2, that is a gas. And this gas, or dissolved gas as a carbonic acid, is not harmful to the tablets. It's not harmful to the circuits. So when we talk TOC destruction, we are taking, say, in a test loop, we put glycol or we put methanol, we spike the water, and we see how much of that doesn't exist anymore after the UV, meaning it was evaporated as CO2 or stayed as CO2 dissolved in the water. And that CO2 dissolved in the water just goes away. You know, in hydrocarbons, you have hydro, you have carbon. The hydro part just goes back to water. And as I said in the conversation before, you also have those that are some of those hydrocarbons that may be longer molecules. You also want to get rid of them. So TOC reduction means taking the carbon to CO2. And good dosing means also not putting too much UV so you don't create hydrogen peroxide that actually causes corrosion in your systems. I have another question here. Can I talk about recirculation loops? Does the UV dose increase? That's another excellent question. How do we size a recirculation loop? A recirculation loop in general is to protect the UV in a recirculation, is to protect whatever enters the loop. We know that if we had just permeate water, perfect water, that was not getting in touch with anything, just flowing through a pipe loop, getting out of a tank and then back to the tank without doing any function, we really couldn't need a recirculation loop, and we didn't need the UV. What we want is actually to get multiple use of the water that we have in that tank of treated water. And what we need in the recirculation loop is to know what is going to affect the water. Do we have any contact with air? Do we have any contact with processed materials? So the UV is here going to act on that water, and it's going to be mostly on how much pollution you got through the loop. We have our sizing rules on that, and usually how we calculate is we calculate what dose of UV, and is measured in the energy in millijoules, how much energy we're going to put into that water to make sure that there is not a TOC increase or that there is no microorganisms that polluted the water later that we have to control. So a lot of conversation between the user of the application and the sizer, that is in this case us as designers, helps a lot. Most of the time there is enough experience and we know how much a pharma application wants to have in the recirculation loop. So In those cases, we usually have our tables. We work with the millijoules that are standard in the industry, and that's how we size it. Many times, depends on how much flow it goes through. We can also size it by pipe size and just make sure in the dialogue with the client that we are doing the sizing correct. Does is anybody interested in me extending a little bit about smart lamp applications? Where are we going in the future? Okay, I got a yes. So this is a very interesting subject. When we started working, say 50, 70 years ago, when Aquafine was created by Luis Veloz, that left the Westinghouse company and started the first UV applications for disinfection, it was very, very dumb lamps, very dumb systems. It was like when X-rays were used to actually correct size the shoes for a person 100 years ago or 200 years ago. It doesn't matter when. The deal is with UV, it was just put a lamp and make it, and it will work, and the water will be better after than before. The deal is we have been in these 70 years of evolution giving more information, getting more information from the system. Now we measure intensity, we measure flow, we know better, we know for different microorganisms what the sizing should be, how many millijoules actually affect them. And the next step, as I said in some of the conversation, was what are we going to do with overdosing? In one hand, we don't want to waste our energy. In another hand, we don't want to create peroxides. So every time now we are creating lamps, you remember the lamp with David Paul had only a positive and a negative. It was two poles, two connectors. Now we are getting to lamps with 4 and 5 pins, and that means more feedback to a smart panel. Okay? I got a question. Let me try to read it. I will answer. Let me clarify the recirculation question. Suppose the water is recirculated for 10 hours. Since the demand is low, does the UV activity of that water increase? In other words, will it build up in the free radicals? Okay, that's a very good question. And this is a subject that I didn't talk about. Let's talk about residuals, and let's compare what is the common chlorine or UV. Radicals are created, but radicals are also very short-lived. If you heat water with UV, having an OH radical and having an H radical, they are very, very short-lived. We can say with almost 100% certainty that after the water leaves the UV chamber or the light traps, those radicals are not anymore there. When a municipal system asks you to have a 0.5 ppm of chlorine at point of delivery, is that we know that the chlorine that you put in the water in your water treatment plant at a level of 3 ppm is going to be used depending on what is in the line to a level that will be higher than 0.5 of ppm at the point of use, meaning the chlorine will flow through and will make other compounds, but it can flow through for miles or kilometers and deplete very slowly. UV, if you turn on the UV in the recirculation loop, and then you turn it off, you will not have any free radicals. So if you get pollution on microorganisms, after you turn off the UV, there will be no UV residuals and no free radicals taking care of those microorganisms. So any system that is open to pollution with microorganisms have to keep the recirculation going and have to have the UV lamp on. Next question, did I understand that LPUV will destroy chloramines? I seem to recall MPUV will not. That's correct, LP will do. Okay, and the chloramines, we have our software, and we size units for chloramines continuously, and also for chlorine dioxide. We can help you in actually sizing a system if you need one.
Well, thank you very much, Simon. You've gone right up to where we want to end. So I'm just going to do a minute to wrap up. But again, thank you, Simon, so much for the valuable information on the LP UV. So if you have a question, you think of a question that you didn't ask, you can go ahead and contact Simon. Here's his email address. And again, you'll be receiving a PDF in the next day or two of the presentation. So you'll have his email address. Also, just for your information, DHP has lots and lots of training, including UV training. So if there is anything that we can do for you in the form of training or technical services, please contact us. So again, thank you all for attending. And when you get off of the webinar, you'll receive an email. There'll be 3 questions. It will only take 10 or 30 seconds to answer. It basically is just giving us feedback of what you thought of this webinar. So thank you so much, and we'll see you at the next webinar. Bye-bye.
Thank you, everybody, all the attendees.